Hey guys, today we will do 8.7 numerical integration. So far we learned integration techniques, how to take the integral of certain functions, but it might happen that sometimes uh, it's hard to integrate and find exact integral. In those cases, we might try to do numerical integration, which is approximate, right? It's never exact. It's going to give us approximate integration, and if you're happy with approximate integration, then numerical integration would work. Learning objectives are we discuss trapezoidal approximations, then we discuss another method called Simpson's rule, and finally we will discuss error analysis. As I mentioned, numerical integration gives us approximate values, but how far are we from getting exact? So we need to know this error estimate, right? Okay, so let's get started. Okay, so what is trapezoidal approximation? Well, how do we define the integral? We defined integral using Riemann sum. And what was the Riemann sum? Riemann sum was something about approximating an area using rectangles, right? We approximate area with rectangles, and if we keep improving approximation by dividing the interval AB uh, into a large number of partitions, eventually in the limit we will get exact integral, right? So in fact, you can also do for the numerical approximation, you can simply do this Riemann sum approximation. You can take n large enough, and then it will give you some sufficiently nice approximation. That's possible. However, somehow trapezoidal approximations and the Simpson's rule, they give a better approximation for fewer intervals n. So what is the trapezoidal approximation? Well, trapezoidal approximation is, as the name suggests, you're trying to approximate an area using a trapezoid instead of you see, for the Riemann sum we would either, for example, for the first one we would either take this part, or we would take, for example, that part, right, for the right, or we could take something in the middle, and we would approximate with such rectangles. However, for the trapezoid approximations, I simply take this trapezoid, right? And I'll calculate its area. So what is the area of the trapezoid? Well, the trapezoid means two sides are parallel, and h is the height right here. So the area is a plus b. So the sum of the bases divided by 2 multiplied by the height, right? So in our case, the trapezoids are sort of vertical, right? And we have the height is already given, so our height in this case is delta x, right? So if you want to calculate, let's say that ith interval, right? Let's say somewhere ith interval, then the area of that particular trapezoid would be the sum of these two bases multiplied by delta x divided by 2, right? So if let's say this is yi, if this is yi plus 1, then this area, small area, would be yi plus 1 divided by 2 times delta x. Okay, so then let's call it capital T here. So what is the first one? First one is, oh, by the way, what are these yi's? Well, yi by definition, this is given for the function. This is f of xi. And xi, you know the formula, right, for xi. So xi would be a plus delta x times I. Okay. So then what would be the first area of the first trapezoid? Well, it would be here, let's call it y0. So it would be y0 plus y1 divided by 2 delta x. What would be the second one? It's y1 plus y2 divided by 2 delta x. so forth, right? What would be the last one? Last one would be yn minus 1 plus yn divided by 2 delta x, right? So what you see is, for example, this y1 is repeated twice, right? So here I have y1, here I have y1, but they're divided by 2. So in the sum, when I take out the delta x, what we see is something like this, right? So it's y0 divided by 2, but then y1 is just y1. There is no division by 2, etc. So you go up to yn minus 1, but then yn would be again divided by 2, and then you multiply by delta x, right? Another way would be you can take out 1 over 2, then it will be y0, 2y1, etc., 2yn minus 1, then yn delta x. So for any n, that would give you some approximation, but it will be better than Riemann sum approximation. So to sum up what we have, if you want to approximate an integral from ab of f of x, then this capital T will give an approximation for the integral where I define xi's as in here, and while delta x is b minus a over n, so the length of each subinterval, right? And as I said before, yi's, we pick it to be f of xi's. Okay, so let's do examples. All right, so applying trapezoidal rule for with n equal to 4 to the integral x squared from 1 to 2. So let's first calculate exact solution because we want to compare dx. So here we get x cubed over 3 evaluated from 1 to 2. Well, we get 8 over 3 minus 1 over 3 gives 7 over 3. This is exact solution, right? Exact value for the integral. Now let's apply trapezoidal rule, where we take n equal to 4, which means delta x is going to be, which is b minus a over n, we're going to be 1 over 4, because b is 2, a is 1, so b minus a is 1. All right, now I need to determine my partition, right? So what is my x0? My x0 is 1, my x1 is 1 plus delta x, so this is 5 over 4, x2 is 6 over 4, x3 is 7 over 4, and finally x4 is going to be 8 over 4, which is 2, right? And now I need to find yi's, right? So what is yi? Well, yi's are determined by the integrand x squared, right? For each partition value, I get these yi's. And then, according to trapezoidal rule, this integral approximately 2 times y0, 2y1, 2y2, 2y3 plus y4 multiplied by delta x. So this is y0 is 1, y1 is 25 over 16, so this is 25 over 8. Then it's 36 over 16 multiplied by 2, so 36 divided by 8. Then it's 49 divided by 8, and then I have 4 multiplied by delta x, which is 1 over 4. This gives me 75 over 32. Okay, so now we can go ahead and compare the two, right? So the error, if you like, the error in approximation, let's take it in absolute value. So 7 over 3 minus 75 over 32. If you calculate it, it's going to be 0.004 or something. So it looks like even with n equal to 4, we get somehow very nice approximation, right? So the thing that we got, 75 over 32, with a numerical method, gives a very close estimate to the exact value. So this is especially handy if the integral is hard to find, right? If we don't know the antiderivative, for example. Okay, so the next one is Simpson's rule. What is the idea behind Simpson's rule? It's about approximating the area with a parabola. So you pick this area for two partitions and you try to approximate the parabola. Okay, so it sort of gives you something like this, and you sum them up, you get the Simpson's rule. So I will not give you the details, just the result itself. Okay, so this is the Simpson's rule. It says if you'd like to approximate integral from ab of f of x, then it can be approximated by the following quantity. So delta x over 3 and then the y0. So you have y0 and yn as before, but then the coefficients of other terms alternate. 4, 2, 4, 2, 4, 2, and so forth. Okay, and the xi's are as before, and the yi's are again as before. So yi's are found by the formula f of xi. So let's do example. So let's use Simpson's rule with n equal to 4 to approximate the integral of 5x to the 4 from 0 to 2. With n equal to 4, which gives us delta x equal to, so 2 and 0 over 4, so 1 half. Hence, my x0 is 0, my x1 is 1 half, my x2 is 1, x3 is 1 plus 1 half, so 3 halves, and finally x4 is 2. And then I need to find, using this 5x to the 4 formula, I need to find the y values. And then what I get is the integral is approximately, so delta x over 3 y0 plus 4 y1 plus 2 y2 plus 4 y3 plus y4, right? So this is delta x is 1 half, so this is going to be 1/6, y0 is 0, 4 y1 is 5 divided by 4, 2 y2 is 10, 4 y3 is 403 divided by 4 plus 80. So this is 32 plus 1 over 12. What would be the exact? Well, exact value, you can integrate 5x to the 4, which is x to the 5 from 0 to 2, which is 32, right? So we see that the error that we are making by Simpson's rule is 32 minus 32 plus 1. So 32 minus 32 minus 1 over 12. So this is only 1 over 12, right? So again, with using as few as n equal to 4 subintervals, we can get quite a nice approximation. So this is relatively small for n equal to 4. So again, we see that the Simpson's rule is another nice way of approximating integrals. Okay, the error analysis. So the theorem states the following. Let's assume that our functions are very nice, that they have second derivatives, that continues, and so on and so forth, right? where m is upper bound for the second derivative on this interval. Okay, because continuity, we know that by extreme relative, we know that such bound exists. Anyway, let's call et to be e sub t to be the error estimate. Then the theorem says that error using trapezoidal rule might get as worse as capital M times b minus a cubed divided by 12n square. So basically, we can control this error by letting n large, right? Because this is n square. So we can always do, as far as we know how to bound capital M. Okay, how about the Simpson's rule? Let's call capital E sub s to be the error coming from Simpson's rule, right? Okay, so in here we assume that the function has fourth derivative and continues, so in particular it has some upper bound capital M, then the error can be at most capital M times b minus a to the power 5 divided by 180 times n to the 4. You see, somehow here we are doing even better, n4, right? So if we increase n, this error very soon gets very small, right? So we can sort of control it. Okay, so let's do a couple examples on this. All right, find an upper bound for the error in estimating this integer right here using the Simpson's rule. So this is an example that we did in the previous slides. So let's recall the error estimate from the previous slide. So to estimate this ES, I need to know capital M, right? And then I'm done. So what was the capital M? Capital M was the upper bound. So you can think like M to be, if you like, the maximum of the fourth derivative, yeah? The fourth derivative, where x is on this interval AB, so 0 to. So this is another way to write capital M. Okay, so I need to find the fourth derivative. What is my function? Was 5x to the 4. So if I take the first derivative, I get 20x cubed. If I take the second derivative, I get 60x squared. If I take the third derivative, I get 120x. If I take the fourth derivative, I get 120. So this is just a constant, right? So it means my m is, in fact, I can pick it to be 120 or anything larger than 120, but since I want to make sort of a nice upper bound, I need to take the smallest possible capital M. All right, so then ES, this error, with using N4 gets as bad as 120 times b minus a is 2. So 2 to the power 5 divided by 180 times n to the 4. So 4 to the 4. If you compute it, you get 1 over 12. This is, we got exact, right? So in the previous example that we did, we indeed get 1 over 12, and the reason why we are getting exact is because we are not really trying to find maximizing f, it's just equal, it's constant, right? All right, in example 4, we want to estimate the minimal number of subintervals. If you remember from error estimates, we know that if we increase the interval, number of intervals, namely n, little n, then the error gets smaller and smaller, right? So let's say that I want, in the Simpson's rule, I want my error to be less than 10 to the minus 4. In the previous example, when I picked n equal to 4, the error was 1 over 12. So let's say that I'm not very happy with 1 over 12. I want to make it better. So I want to find what is the right n to pick so that I'm sure I can make sure that the error is going to be less than 10 to the minus 4 in the previous example. So for the Simpsons, we know that the error is approximated by capital M, b minus a over 5 divided by 180 times n to the 4. So if I manage to make this one less than 10 to the minus 4, then automatically the error also becomes less than 10 to the minus 4, right? So this is what I'll try. What is m? M is 120. b minus a is 2, so this is times 2 to the 5, divided by 180 n to the 4. So I need to determine n, right? So n is the quotient here, 10 to the minus 4. So from here, what I see is n to the 4 must be more than, so I can cancel some things. I get 18 times, sorry, so 12 times 32 times, okay, 10 to the 4 divided by 18. Okay, so this implies if I take sort of the fourth root of both sides, what I get is, this implies that n must be more than this quantity right here, whatever it is. So 12 times 32 times 10 to the power 4 divided 18. So this is roughly 21.5. So I need my n to be more than 21.5. In particular, I could take, for example, n to be 22. So this is the least, the minimum n number of interval that I need, 22. Then I can guarantee that the error will be less than 10 to the minus 4. So you can take more than 22. You can take 23, 25, 30, whatever. If you take more, the error will get better. But then your calculation gets more involved, right? So it becomes much larger than what you would do with n equal to 22. I'll stop here.